This video starts our journey into number theory. Luckily, we won't be dealing with crazy numbers, only this one particular set. It's got a strange looking n, but it's the set of natural numbers. They start at 1 and they go on and on forever. These are the natural numbers. Now, while we are not going to be doing any division per se, we are going to still be able to tell when one number goes evenly into another number. So n, a natural number, n is divisible by the natural number m if n divided by m has no remainder. In this case, we write m bar n. As some examples, we would write 2 bar 4 because 2 divides evenly into 4, 5 bar 25, 7 bar 35, etc. Notice, no matter what, the number 1 goes into any number. So 1 always divides evenly into anything. We also have notations for if something doesn't go into it. Say like 5 would not, or 29 would not be divisible by 5. I would use a slash through the notation. So 4, for example, does not go evenly into 9, etc. Furthermore, if a number m is bigger than n, then it's not possible for m to go into n. So we obviously have this not divisible symbol as well. Now, if m goes into n evenly, then n will equal m times some other number, k, where k is a natural number. So as an example, we have 5 divided evenly into 35, and we know that 35 equals 5 times 7. So in this particular instance, k was equal to 7. 6 goes into 12 evenly. 12, as we know, equals 6 times 2. So in that instance, k was equal to 2. So the k will be dependent on the problem at hand. 13 divides evenly into 39. So 39 equals 13 times 3. Here, k was equal to 3. Definition: natural number is prime if it only has exactly 2 distinct divisors. So as an example of some of these numbers, 2, 3, 5, 7, 9 does not count as one of these numbers. I'll show you in a minute why it does not. 11, 13, 17, 19, 23. This list actually goes on forever, but these numbers are difficult to find many times. But one of the reasons like 9 is not prime, because look at the numbers that go into it. Its divisor list are 1, 3, and 9. That's more than 2. 1 is not prime. Its list of divisors is just 1. Remember, we're sticking in the natural numbers, so don't think about negative numbers. So it doesn't have enough divisors to be considered a prime number. While 9 is not prime because it has too many divisors. So many times you'll be asked to check if a number is prime, and it'll be necessary. So as an example, let's check one. Is 57 a prime number? Now, your calculators were supposed to have on them, they're scientific calculators, well, they're supposed to be scientific calculators nonetheless. So I know that on there somewhere is something called a square root. Well, for 57, let me come to my calculator. And my calculator, I have an x squared button. If I go right above that, hit the second, I get a square root signed. I'm going to type 57 and then hit enter. So the square root of 57 is about 7.5. I don't care about the decimal part of it. I'm just going to say it's about 7. All I care about is the natural number part of it, the 7. So I'm going to check these possible numbers to go into 57. I'm going to check all the prime numbers up to 7. So I'm going to check 2, I'm going to check 3, 5, and 7. I need to go no further than that. So if I try to do 2 into 57, it's obviously not going to work because 2 is even and 57 is odd. So that I don't even have a chance at that one. Next, let me try 3. This is long division. 3 will go into 5 one time. So that's 3 goes into 5 once. Put the 3 down below. Subtract 5 minus 3 is 2. And then 3 goes into 27 9 times. So it did break down because my remainder here is 0. So 3 goes into 57. I absolutely wrote the wrong thing. 3 divides evenly into 57. Since we found a divisor that was not 1 or the number itself, we know the number is not prime. So one thing about prime numbers, any prime number only has itself and 1 as divisors. Another definition: a natural number greater than 1 is called composite. If it's not prime. From the example that we just did, 57 is a composite number. 73 is prime. How do I know? First thing I'm going to do is take the square root of 73. and I get roughly 8. So I only need to try the prime numbers up to 8. So my prime's up to 8. We have 2, 3, 5, 7. So those are the only things I have to try to see if they go into 73. I'm going to make it easy on myself and on you. Just let the calculator do it. So let me pull it over to the side so we can see. I'm going to do 73 divided by each one of those numbers. So if I start with 73 divided by 2, do you see I get a decimal? That means the remainder was not 0. Let me try again. 2. Oh, I made a mistake. That's not what I wanted. Next want to do 73 divided by 3. Once again, that decimal indicates that there is a remainder. All right, let's try 73 divided by 5. I shouldn't even have to do this one. You should know that it's not going to be an even division because 73 doesn't end in a 5 or a 0. So you know this is going to have some sort of a decimal. And then finally, the last one I have to try is 73 divided by 7. And you can see, no matter what I try, I always get some sort of a decimal. So it was never an even division, or none of those divisions had 0 remainder. So what we did by showing that is I showed that 2 did not go into 73, 3 did not go into 73, 5 did not go into 73, and 7 did not go into 73. That implies that 73 is prime. Prime numbers are these numbers that sometimes are called irreducible numbers that can't be broken down into smaller factors, have been known since Greek times. Let me show you something that was invented in those times called the sieve of Eratosthenes. And what we do is I'm going to write all the numbers from 1 to 100 down. What I have here is the list of the numbers 1 to 100. And what I'm going to do is, starting at the number 2, I'm going to circle it. Starting at 2, I'm going to count every other number. So every second number that I count, I'm going to cross off, because if I count 2 places to 4, I know 4 is not a prime number because 2 will go into it. So I'll put a slice through it. I go 2 more spaces to the 6, slice it. That's obviously not prime. To the 8, slice it. Go 2 again to 10, slice it. And what you'll see in this way, all of the even numbers will get wiped out of this table. So every column who has even numbers will get wiped away as I count every 2 units. What we're doing here is I'm coming up with a method. I didn't come up with it, Eratosthenes did, that will leave the prime numbers behind when you've done this. Notice that 3 was not crossed out in the process. So I'm going to circle it. Now what I'm going to do is count every 3 places. Starting at 3, I'm going to count every 3 places. 1, 2, 3. 6 was already marked. Now go 3 again. 1, 2, 3. 9 was not marked. Continue on. 1, 2, 3. 12 was already marked. 1, 2, 3. 15 was not marked. So I'm going to go through and take out the numbers that get wiped out by these. They're all multiples of 3. So 21, for instance, 27, 30 was already taken care of, 33, 39, 45, 51, 57, 63, 69, 72 was already done, 75, 81, 87, 93, and finally 99. So those were all the multiples of 3. Notice that 5 was not canceled. I will circle it. Now I'm going to count every 5 places and mark those off. So starting at 5, if I go 1, 2, 3, 4, 5, the 10 has already been marked. Continue on. 11, 12, 13, 14, 15. 15 was already marked. 16, 17, 18, 19, 20 was already marked. 21, 22, 23, 24, 25. 25 was not marked. I can cancel it. Continuing on. 30 was already marked, but 35 was not yet marked. In fact, looking down this column, anything that ends with a 5 is going to get wiped out. So I might as well do that now. And so doing this, I've wiped out all the multiples of 5 on this table. This column took out all those that had 5s in the end, and when we did 2, it took out all of these with 0s as the last digit. Now I move on to 7. So I circle it. Count every 7 places from 7. So starting at 7, if I count 7 places, I land at 14. Notice that it's been marked. If I count 7 more places, I land at 21. Notice that it has been marked. 7 more places to 28, it has been marked. 7 more places to 35, it has been marked. 7 more places to 42, it has been marked. 7 more places to 49. Finally, we get to one that hasn't been marked. The reason for that is the smallest divisor of 49 is 7. All the other numbers had smaller divisors than 7. So I can wipe out 49. Now continue on. 7 from there is 56. 7 from there is 63, already marked. Then I move to 70. Then 77 was not marked. 84 was marked. 91 has not been marked yet, so there it is. And then 98 was already marked. So there, I've taken care of the multiples of 7. Now I move on. Let's do 11. Every 11 I have to go and mark. So the next one is 22, already marked. 11 from that is 33, already marked. 11 from that is 44, already marked. 55, 66, 77, 88, 99. In fact, no matter what I choose, I'm going to put a circle around 11. 13. If you take the square root of 100, that equals 10. That means I only needed to check the divisors up to 10 of prime numbers. So the possible divisors that I would have tried up to 10 were 2, 3, 5, and 7, because 9 is prime. So any numbers remaining are prime numbers here. Prime numbers do not have any possible rhyme or reason as far as a formula is concerned. You simply won't find them. That's why they're so difficult. So the prime numbers that I have up to 100 are all these things that I've circled, and I see I've missed a few still yet. If I've missed any more, I do apologize. I will look through. Special note, 2 is the only even prime number. Which numbers are prime? We have A, 89, B, 83,572, or C, 629. 89 I don't have to do because you already saw in the table here. There it is right there, circled. It's a prime number since it's listed in that table. So for part A, that is prime. For part B, though, that is composite because it's even. Two will go into it, for example. Part C, I don't know off the top of my head if 629 is prime or not. So the first thing I'm going to do is take the square root of 629 and then start testing numbers up to whatever that is. So let me have my calculator back, turn it on, and I will do the square root of 629. That's about 25. So I need to try I should do it this way, trial divisors. I like that better than what I've been saying before. All the primes up to 25. So notice the 2, I won't even bother with 2 because the number 629 is an odd number. 2 is not going into it. So I have 3, 5, 7, 11, 13, 17, 19, 23, and that's it. So I have to try each one of those and see which one, if any, goes into them. Once again, I'll let my calculator do the bulk of the work for me. So we'll start with 629 divided by 3. Now I know it's not going to work because if you add up the digits for 629, 6 plus 2 is 8 plus 9 more is 17. 3 doesn't go into 17. So I know that this thing is going to end up having a decimal. And I was correct. So I can forget about 3. Let's move on. Now I can obviously forget about 5 because the last digit for 629 is neither 0 or 5. So I can scratch that one as well. Now the other ones, I'm not really so sure. So let's go ahead and do 629 divided by 7. And I have a decimal, so 7's not going to work. 629 divided by 11. 11's not going to work. 629 divided by 13. 13's not going to work. 629 divided by 17. Aha, it works. So 17 worked. So that guy. So 629 equals 17 times 37. So 629 is composite. Next topic is something called divisibility test. So I have a collection of divisibility tests. So we'll look at divisible by, and when. So we have tests for several things. 2 is even. 2 is easy, I should have said. When the number is even. So that's easy enough to see. The last digit is 0, 2, 4, 6, or 8. Divisibility test by 3 is interesting. If the digits add up to be a multiple of 3, then 3 is a divisor. We'll do examples after I get these all cataloged. For 4, the last 2 digits are divisible by 4. Divisibility by 5, the last digit is 5 or 0. 6, divisible by both 2 and 3. 7, we don't have an easy test for that, so I'm going to bypass it. 8, last 3 digits is divisible by 8. 9, if 9 is a divisor of the sum of the digits. Just like 3, you add up the digits and see if 9 goes into that number. For 10, the last digit is 0. 11's another bad one. 12, divisible by both 3 and 4. Let me illustrate all this with an example. We'll start with 2 is a divisor to 48, since 48 is even. 3 divides evenly into 597 because 5 plus 9 plus 7 equals 16 plus 5, which is 21, and 3 is a divisor of 21. 4 goes into 328 because 4 is a divisor of 28. 5 is a divisor of 655 because 655 ends in a 5. 6 is a divisor to 690 because 2 is a divisor of 690. 690 is even. 3 is also a divisor of 690. 6 plus 9 equals 15, and 3 is a divisor of 15. 8 goes in evenly into 5,136 since 8 is a divisor of 136. 8 goes into 136 evenly. 9 is a divisor of 5,130 since 5 plus 1 plus 3 plus 0 equals 9, and 9 is a divisor of itself. 10 is a divisor of 293030 since 293030 ends in a 0. And finally, to finish off the last example, 12 goes into 840, since 3 goes into 840. That's because 8 plus 4 plus 0 equals 12, and 3 is a divisor of 12. And 4 also divides evenly into 840 because 4 is a divisor of 40. The next topic is prime factorization. Let me start with a number to show you how it works. I'm going to start with 36. Now 36 is a multiple of 2. So I know that I can write 36 as 2 times 18, like that. 18 is even again, so I can pull a 2 from it as well. So now I have 2 times 2 times 9. Well, I can break that 9 down. I can't break this down any further. So this is what we'd call the prime factorization. That means you break the number down into its prime components. Another way of writing this, so there's one way. We have 36 equals 2 times 2 times 3 times 3. Or you can also do this, 36 equals 2 to the second times 3 to the second. Either way, it's showing all the primes that are involved in the composition of 36. I'm going to do that again, but I'm going to use something called a factor tree. You have almost certainly seen this before in your life, but here's the way I do them. I start with my number 36 that I want to break down into its prime factorization. First thing I notice is that it's even, so I'm going to divide it by 2. 2 is a prime, so I'm going to circle it. 36 divided by 2 is equal to 18. So I'm going to work this, I'm going to pull this back down pretty much the way I did up here. I'm going to keep breaking down the part that can be broken down. So 18 also happens to be even, so I can break it down into 2 and 9. And then finally, 9 is odd, but also can be broken down into 3 times 3. So all those circled numbers are the prime numbers. The answer that they'll want you to give is something along this lines. That which is circled is the prime factorization. So let's do another example with more complicated numbers. Find the prime factorization. A, I have 306. B, I have 605. And C, I have 1035. So we'll start with part A, 306. Take it easy on yourself. Use all those rules that I gave you right before this, the divisibility tests, to help you do this. For example, 306 is an even number, so I know that 2 goes into it evenly 153 times. Now 153, if I look at these digits, 1 plus 5 plus 3 is 9, and 3 goes into 9. So I'm going to divide it by 3. I might need to do work on the side. You can use your calculator to help you out with this process. I want to do 153 divided by 3. $51. Well, 3 goes into 51 because 5 plus 1 is 6. So I can just keep using my calculator for this. Now I can just go divide by 3 again, and we get 17. 17 you should recognize by now that it's a prime number. So my answer then is 306 equals 2 times 3 to the second power times 17. You can always check yourself. Let me come back to my calculator here, and I can always punch this into the calculator and see what happens. So I had 2 times 3. If you want, you can do 3 times 3 or 3 squared. It really doesn't matter. And let's see if I get my original number back. There is 306, so I've checked myself. Part B, we have 605. Divisibility tests tell us that 5 go into that easily. What's left over? Well, let's have my calculator tell me. I'm going to do 605 divided by 5, and we get 121. 121, what goes into it? 3 is not going to go into it because 1 plus 2 plus 1 is 4, and 3 doesn't go into 4. No even number is going to go into it. 5 is not going to go into it because it doesn't end with a 0 or a 5. 7, I'll try 7, see what happens there. So I'll try my 121 divided by 7, and what do I get? A decimal. 7 doesn't work. Well then, let's try 11 is the next prime number after that. Ah, 11 goes into 121. And in fact, 121 divided by 11 equals 11. So I know that 121 is 11 times 11. And those are, well, 11 is prime. So my answer here is 605 equals 5 times 11 to the second power. Finally, my last one was 1035. Once again, I see that 5 there is so easy. I'll use it. Let me have my calculator back. I'll do 1035 divided by 5. I get 207. Well, that's lucky because 2 plus 0 plus 7 is 9, and 3 is going to go into that. So I will divide this number by 3, and I get 69. Well, 3 goes into 69 because 6 plus 9 is 15, and 3 goes into that. So let me divide by 3 again. $23. 23 is a prime number. And so 1035 equals 3 squared times 5 times 23. That's my answer.